Hello and welcome everyone to today's Critical Conversation event. My name's Hayatan Salim and I'm the CEO at the Royal Academy of Engineering and the Queen Elizabeth Prize for Engineering Foundation. And it's my very great pleasure to be hosting another of these online fireside chats that we run to explore topical issues that are important for engineering and for society. Our overarching goal at the Royal Academy of Engineering is to harness the power of engineering to build a sustainable society and an inclusive economy that works for everyone. And we've used these critical conversations to look at some of the engineering challenges and opportunities that will be crucial to addressing this goal. In March 2023, the UK government published its Science and Technology Framework, which set out, and I quote here, the 5 technologies that are most critical to the UK: quantum technologies, semiconductors, engineering biology, artificial intelligence, and telecommunications. And over the next 5 critical conversations, I'll be joined by an array of brilliant experts to help us understand what these technologies are, why they matter, and what we need to do to capture the benefits and manage the risks. Today, we're going to be focusing on quantum technologies. These technologies take advantage of phenomena at the atomic scale to enable new ways to manipulate information. And this is very much about quantum technologies, not quantum technology. Quantum sensing, quantum imaging, quantum computing, quantum clocks, quantum networks, quantum communications are all encompassed by the term. And while we're not going to be able to cover all of those in detail today, we will aim to give you an overview of the field and dig a bit deeper into a few of those areas. I should also say that quantum is a field which generates as much confusion as it does excitement. And as is the case for many disruptive technologies, there are a range of views, even among experts, about both the engineering realities today and the opportunities for tomorrow. So to help us make sense of all of this, I'm delighted to be joined by Professor Melissa Mather, who is Royal Academy of Engineering Chair in Emerging Technology and Professor of Quantum Sensing and Engineering at the University of Nottingham, and Academy Fellow Professor Peter Coveney, Professor of Physical Chemistry at University College London. Melissa, Peter, welcome. Thank you for joining us. I've got a few questions to start the conversation, and then we're going to open up to questions from the audience. So please do pop your questions into the comments box, and I'll try to make sure we get through as many as possible during the course of today's event. So I'm going to start with you, Melissa, first. Could you please give me an introduction to your area of technology? Tell us a bit about it, how it works, and why it matters. Over to you, Melissa.
Oh, great. Thank you. And delighted to be part of this conversation and looking forward to interacting with everyone's questions. So the area I work on is quantum sensing. And the component that we use is the fragility of quantum states to the external environment. So the quantum sensor is exciting because it can help us measure the world around us. And we can look at things such as sensing magnetic fields or electric fields, or maybe chemical reactions going on in the body. And what's exciting is we can measure these around 1 billion times better than with conventional sensors. And it's the reason behind this is because, as you've alluded to, the quantum mechanics that underpins how these sensors work. These quantum states we use are quite fragile. And this can be quite troublesome for people who are wanting to build quantum computers because they want to encode information in these quantum states. So if that state's destroyed, it's very tricky. But for me, working on quantum sensors, it's brilliant because it means that this fragile state is so sensitive to the surroundings that we can actually harness it as a benefit. And there are many types of quantum sensors, and they use different quantum objects. So some are using atoms, some use ions in atoms, some use electrons, some use photons. And in my work, the quantum object is actually an atomic scale defect in synthetic diamond. So we all probably know that the diamond lattice is made up of carbon. And it turns out that if we replace some of the carbon with a nitrogen atom, and nearby we have an empty space, we get this defect. So basically, it's a defect in the diamond. And we all probably have realized that if you're going to buy someone maybe a gift of a diamond, that you happen to have to pay a lot more money for the clear and sparkly diamonds. And when we've got a defect, it gives a bit of a color. But for us, that color is again what we want. And it turns out that we can control this particular atomic defect with light. And we can also read out the quantum state with light. So it's a really convenient platform to us to use. I should also mention that the other advantage of using the defect in the diamond is that the diamond acts as like a sort of a shield to keep the quantum state for a bit longer. So we can make our measurements at room temperature, and sometimes other quantum sensors have to have their measurements quite cold. So this is another advantage for us. So really, the work we do in my lab, we're sort of standing on the shoulders of giants, of people in quantum physics who have sort of developed and discovered these sorts of defects. But what we're trying to do is deliver this as a real engineering solution. We're trying to address challenges of actually how do we engineer this into a device which captures all the light that we need? How do we introduce these into things like living cells and actually have it as a device that could be deployed by non-specialists? So guess why does it matter? So we're sort of working in two particular spaces at the moment. One is in the life sciences. So we're working with people who are trying to look at developing new MRI contrast agents. So we're able to, in a little dish, study how cells interact with these chemicals. We're also able to study the biological reactions that happen as we age or during disease, which generate free radicals. So we're sort of able to look at the, reactions involved in making energy in cells. And then the other thing is we're looking a bit wider now, looking at how we can impact on, the work towards net zero. And we're looking at photocatalytic carbon dioxide capture, and so how we can help understand this chemical process better. So I hope that gives a bit of a flavor of the work we're doing and how, as working in an engineering domain, we're trying to translate the findings in the fundamental physics to address some real world use cases.
Brilliant. Thank you so much, Melissa. We will certainly pick up on some of those themes in a minute, but Peter, we'd love to hear a bit about the technology you work on too.
Thank you very much indeed, and for inviting me to participate in this very interesting discussion. So my current area of interest here is in seeking optimal ways of using quantum devices. When I say a quantum device, I really mean a quantum computer that might reveal new ways, faster, bigger, better, as it were, to perform what we call molecular electronic structure calculations, and those that can go beyond what is possible on conventional computers. And I need to explain why and why it matters. But Melissa was already referring to some degree obliquely to the atomic and molecular aspect of this, because if you ask why molecular electronic structure calculations are important, well, all matter is quantum mechanical at root, and the substances of which the world is composed, and in engineering we make use of, are ultimately composed by molecules at their most basic level. So everything of interest in engineering, right up to the largest scales, ultimately sort of depends on and is controlled by what's going on there. So it would be really nice, would it not, if we could actually calculate those materials properties using quantum mechanical methods. We would be home and dry in designing all manner of things, from drugs and various other medicines, designing batteries, catalysts, something Melissa mentioned really to do with carbon capture and storage, to automotives and aeroplanes and so on. The reality, though, is we can't do this, and the question arises as to why not. And fundamentally, it's because although quantum mechanics is ruling the microscopic world, the systems which it's trying to describe, even in those terms, are very complicated. And evidently, we have to use computers to address and solve those problems. And the computers we're talking about normally are what in the quantum world we call classical computers, and I just tend to call conventional ones. So their problem is when they try to solve these types of electronic structure problems, which would tell us the solution to all those challenging questions I posed, they rapidly run into the sands, because attempting to calculate all the interactions between these vast numbers of electrons whirring around the molecular entities just starts to become intractable. Meaning that it's the computers we have today, even the fastest ones and the largest ones, cannot solve these problems fast enough and for big enough systems to be relevant. And if we try to build bigger molecular systems in this way, the approximations start to become unreliable. So the great hope with quantum computers is that we can accommodate these full electronic structure calculations. And in that sense, initially, we mean things like the very stable or ground state nature of collections of atoms in molecules or other materials using quantum computers, because in principle and theoretically on a quantum device, you can handle problems of arbitrary size only in a sense that's linear in the size of the problem, where the size might be the number of electrons that it contains, rather than depending exponentially on that number, which happens in a conventional computer. And if that's possible, then you start to be able to think of studying really very large systems with thousands of atoms and millions of electrons in them. So that's what we would like to do. And a large part of what goes on in quantum computing is theoretical work, which holds out the potential that we might achieve that kind of quantum advantage. And the question is, how can we actually realize that advantage, namely to solve those problems which today are completely intractable using modern quantum hardware? So what goes on in quantum computers, they're made up of qubits, and these things are the quantum equivalent of the bits, digital bits in a classical computer, and they measure the size of the computer we can wrestle with. How big are the machines we can work with today? Well, actually, most of them, you might be shocked to know, have only a handful of qubits on them. And the biggest such devices are ones that are being built by IBM. Today, 127 qubits is the largest device. When you think of the biggest supercomputers that are exascale conventional ones, they have, up to millions of cores on them. So in those terms, we're nowhere near the same scale. IBM will have a 433 qubit device soon, and maybe 1,000 qubits in the near future. This all sounds very good compared with most of the other manufacturers who have literally 3 to 5 or maybe 12 such qubits available. But the problem is the current technology for these devices is extremely primitive. The qubits typically are based on the IBM ones on superconducting technology. They have to be kept very cold, but even so, and related to what Melissa was saying, the sensitivity of the quantum states to the devices means they have very high noise levels. And that means when we start to do calculations that involve multiple qubits, the fidelity of the calculations and the signal versus the noise in the calculations starts to diminish very rapidly, such that today it remains the case that it's very difficult to get any type of calculation to come out of a machine that is using more than of the order of 5 or 6 qubits, which is a tiny number. And the severe limitations of these devices, we're called NISQ ones, which are the sort of noisy intermediate scale quantum devices. These are the ones we work with, are constantly for the user a battle, reducing to the minimum number of qubits any problem in order to be able to put it onto such a machine and then calculate with it. And that uses, for us, a combination of theoretical methods of a variety I'm not going to go into now, to the extent that we can reduce the qubit count to a minimal number and then impose various techniques such as noise reduction and error mitigation strategies to find the signal in the noise. Today, we're able to do this to some degree up to of the order of 5 qubits for our electronic structure calculations, which puts us in an area where we're just about competing with some basic interesting quantum chemistry calculations, but we have so much further to go. That's the challenge, the importance and the difficulty.
Peter, thank you very much. You've given us quite a lot to digest there, and we're going to develop some of those thoughts a little bit further. But I think before we go on, maybe we should just turn to you, Melissa. Can you help us? There's a lot around quantum technologies that can be quite confusing for people who aren't experts. And we've already talked about qubits and quantum states and quantum objects, and there are QOPs and there are QPUs and all sorts. Can you just take us to the basic building blocks of quantum literacy that will help everyone listening, just to make sure we've got a sense of what the fundamentals are? Thanks.
Yeah, I think this is, thank you. And I think that's a really important topic, because as the quantum technologies advance, then they'll become inaccessible if we don't have a shared vocabulary and a way in which we can talk about them. And I think it's important at this point to perhaps flag that we're already living and interacting with quantum technologies. So the foundation of semiconductors and transistors are using a quantum effect, and we're quite all familiar with lasers, which again use quantum effects. And we should be mindful that when people are now talking about quantum technologies, they sometimes have coined a phrase called quantum 2.0. And this is using different quantum mechanical phenomena. And generally, when people talk about this quantum 2.0, they're talking about technologies that are leveraging quantum mechanical effects of superposition and entanglement, for example. So I think it's the first starting point is to know that we have almost this quantum tech 1.0, and now we're moving to quantum tech 2.0. So and I think it's just to be clear, when people are talking about the technology, then that can help the conversation. So I think in terms of understanding what's going on, I'm not so sure that I fully understand what's going on, but I can understand that we're using these quantum mechanical properties, and we're using them to do things that classical systems can't do. So I think that's a big distinction. It's not like we're just like enhancing the sensitivity or making your Excel spreadsheet run faster, for example. We're using these things because they can solve problems, and they can make measurements that previously weren't possible. And so I think that's sort of another thing to bear in mind when we talk about that. So I think a useful starting point is to have some awareness of some concepts in quantum physics, such as superposition, this sort of idea where particles or the quantum object can exist in multiple states at the same time. This idea of entanglement, where you've got a situation which two or more particles are linked, and so if you know something about one, that you're linked, then you can understand information about the other. Another important thing to have a bit of knowledge about is also, as Peter was talking about, is the sensitivity to the environment and something called decoherence. So we use in these quantum technologies coherence, and so if we have a disruption of this coherence, then we end up perhaps getting errors in our errors in the quantum computation, or we find that we can't measure for as long or as well as we thought. So I think the first building block is just some awareness of this quantum physics. I think the next thing that's important is to, I think especially to talking about engineers and hoping to grow the quantum ecosystem, is an appreciation of the enabling technologies. So a lot of enabling technologies are common, regardless of quantum sensing or quantum I should say quantum computing. So for example, some of these approaches will use semiconductors, some will use optics, photonics, and so we've got a commonality, like we have we also use nanotechnologies and nanoelectronics. So I think having a bit of an understanding of the enabling technologies is also quite good. And I think a key enabler to help discriminate perhaps between the hype and the hope is to have an understanding of the maturity of the quantum technologies and the limitations both scientifically and practically. So, you know, we've got some technical challenges that need to be addressed. But we've also got practical challenges, and I think we also need to make sure that quantum technologies aren't just doing something different or solving a really hard problem. We need to make sure they're solving useful problems. So I think that's sort of maybe the guide star we should be working towards.
Brilliant. Thank you, Melissa. That's really helpful. I can see some questions coming in, so I hope that we're going to get lots more questions, which I will come to very shortly. Just want to pick up on a couple more points, first of all, with you, Melissa and Peter. Melissa there was mentioning hype and hope, and Peter, I know you've got quite strong views about some of this, so I would welcome your comments on where are we in terms of timelines for impact. You know, let's look at the realities behind the rhetoric. And actually, whilst I've got you, as it were, I'm going to smuggle in a question about this interplay between quantum technologies and AI and machine learning, because there is quite a lot out there saying, you know, the combination of the two is going to be as disruptive as anything that we have seen. So, Peter, welcome your thoughts on those.
Okay, thanks very much. The first question about where we are versus where we'd like to be, I think I'm happy to be quoted as saying I've never in my career as a scientist seen a greater divergence between the hype and the reality than exists in the quantum computing domain today. It's great in a way because it's all very exciting, but the differential between the expectations and what we can achieve currently is shocking. As I mentioned earlier, you know, with 5 qubits to extract some results from a quantum calculation, you're only just beyond a pencil and paper, because with 3 qubits, it's an 8x8 matrix calculation. You can more or less do that by hand. So we're not actually doing anything really substantial yet. That's what the quantum advantage challenge is. Can we actually reduce the noise level in these systems and get past the limitations of this NISQ era, what we call the fault tolerant era that lies beyond, we hope? So the question now is, how far away is that? And typically the answer to that might be around 10 years. The question in the meantime is, can we keep the thing going in an interesting way by controlling and combating all these error problems? There's error correction theories, there's error mitigation and noise reduction that we're all fighting over. And so in our own case, that's our biggest battle. So, you know, we need larger machines with more qubits, and the very large qubit counts won't necessarily be used in order to do larger problems, but to actually help to assist with those error mitigation strategies. The problem that Melissa mentioned effectively of what you could call the coherence time may not be clear to everyone, but it's related to the time you've got during which the quantum state is still in place. So the superposition is there that can take advantage of quantum parallelism. And again, this may be a surprise to many, but it's typically of the order of microseconds to milliseconds if you're very likely, if you're lucky. What does that mean? That's the time during which you can perform such a calculation. Milliseconds or microseconds, and therefore you have to repeatedly run many of these calculations to get any answers where you need many in order to get the noise levels down. This is the problem we're facing currently, and it's a very real one. So, you know, fault tolerance is the future, and we have to keep working to improve the technology. There's no question of that. And then to come to your other question about AI and this, I think my view is typically what we need is a convergence with conventional computing as well, because, you know, a large high-performance computer is the place in which you can bring components that will be quantum processing units, a bit like GPUs, that could be used to do dedicated calculations in the same way as the GPUs are also beloved of AI aficionados to do machine learning. They run their calculations very quickly. In an environment where you also have lots of other processes available, you can split up an arbitrary problem into a workflow where it points different bits of the calculation to different aspects of the machine. So these machines are already very heterogeneous. So that's the way I think this is going to go into the long-term future, to really benefit from the capabilities. AI versus quantum computing is one thing, because there's an awful lot of hype about AI. But the thing about AI is that it is capable of producing results on large and challenging problems here and now. So it does things which are important and interesting. It typically has an Achilles heel, which is it lacks explanatory power. And if applied without due thought, can lead to biasing predictions, which can be detrimental to individuals. It's a matter of sort of human rights in some cases. We know the EU and the United Nations have got very serious concerns about the use of AI in general. So it's very powerful, but it doesn't have the explanatory power. On the other hand, quantum computers would be more in the style of sort of physics-based methods, but you can see they're hampered by the state of the technology. In the middle between them are these supercomputers that run conventional physics-based methodologies. And I think the conjunction of those will become increasingly important. AI methods on their own can lead to powerful results, but they are sometimes restricted. If you have them working in combination with something which is, as it were, physics-based, it can ensure, for example, the computations that the AI methods perform are aware of the laws of nature and the laws of physics, and don't just go off making predictions that are not relevant. So I think the integration of all of those is important, and it is kind of happening. The architectures of the big machines are pointing in that direction for AI and conventional computing. The quantum bit is what I'm saying should be brought into play there as an additional component on those resources. And then you'll have an environment which is extremely powerful.
Thank you very much, Peter, for disentangling some of those threads. I would just like to ask a couple of questions about strategic advantage before I go to the audience questions. So, as I'm sure many of our viewers know, the government's launched a national quantum strategy that sets out this 10-year vision and a set of actions that are aimed at making the UK a leading quantum-enabled economy, recognising that wherever you stand on this, quantum technologies are going to be important for our future prosperity and security. And that's part of what's often called the strategic advantage through science and technology agenda, which is maybe not a phrase that everyone's familiar with. So just to be really clear, we at the Academy define strategic advantage as harnessing science and technology purposefully to achieve defined outcomes for security, prosperity, resilience, international influence, and people and environment, with the ultimate aim of conferring comparative advantage for the UK. So, Melissa, I would like to ask you, what is the role of international collaboration in accelerating quantum technology? I've seen estimates that China represents 50% of global public investment in quantum. This is an era where those of us who work in engineering technology cannot escape geopolitics as being relevant to all of us and the decisions we make. And yet we know that collaboration is such a core part of how we innovate and how we make engineering advances. So what is your perspective on how we manage security risks and competition and balance that off against the benefits of collaboration internationally?
Yeah, thanks for the question. So I think, as you alluded to, like, international collaboration is an essential part of research and development. I think it enables us as researchers to interact with people, to diversify the thoughts that we have. And so I think that is a really good catalyst to move basic science forward, and also to move the underpinning engineering forward. So I guess, yeah, that's, as you say, this international collaboration is a tenet of, I guess, excellent research. But as you said, the potential of some quantum technologies is such that we can have great benefits from them, but in perhaps the wrong hands, they can perhaps offer some threats, which we need to be mindful of. Another thing which I think perhaps a lot of people are more familiar with is the shortage of underpinning, like components and elements. People may be sort of aware that there's been a shortage in sort of chips that have been used in computers, particularly as there was a sort of a big demand over COVID times, and there was sort of a supply and demand issue. So I think we need to be mindful there of like, what are the underpinning resources need for the quantum technologies, and where are they? So, you know, if we're looking at some rare earth materials, where literally in the world are they? And how does the UK, who perhaps don't have the geography and geology to naturally have those, how can we secure the supply of that? So, so I think there's elements of ensuring that we look at the value proposition of quantum technologies to the UK. Look at where the UK has strategic advantage in this. And I'd like to point towards really established technologies, such as the photonics industry is so thriving in the UK. We have great skills in compound semiconductors, and really importantly, we're great at advanced manufacturing and aerospace. And so we've got really, if you like, the sort of supply chain, the engineering side, and the use cases. So I think we have great strategic advantage there. And I think in terms of securing and de-risking things, I think that's where we can do a survey of perhaps where we're unlikely to be able to contribute to. For example, we might not be able to have the raw materials. And so that's when we need to look to, you know, our colleagues in policy, and be looking at international trade agreements with various allies that we can interact with. So I hope that's picked up some of the components. I'm sure it's quite a complex situation, and it's moves very quickly. So I think, but we have, I think there are, I think there are precedents for this as well in sort of other technologies. So I think we have lessons learned from other experiences.
Great, thank you, Melissa. Melissa's given us a great overview of the risks that we have to manage, but also some of the strengths in the UK ecosystem that we can harness. Peter, I'd like to ask you a quick question, which is that the UK has committed this 2.5 billion over 10 years for quantum. So if you were in charge of that budget, what would you do with it?
Continuing along the same lines, in terms of the quantum computing and quantum devices that I've been talking about and the interests there, and that's a large and interesting part of this whole quantum technologies issue. It's embarrassing that the UK lacks any significant quantum computing capabilities. I described some of the work we do, and I mentioned the IBM Quantum Hub. I don't get access to that through the UK. I get it through collaborations with colleagues in Europe, not incidentally through the EU per se, but collaborations I happen to have with others that then give us access into the CERN Open Lab technology, and they offer us access to these machines, which you have to pay a vast sum of money. We're talking about hundreds of thousands of dollars per annum to get access to these resources. And we don't have those type of things in the UK. What else do I do? We get access to machines. Again, it's ad hoc through my collaborations with Oak Ridge National Lab in the USA. And there's a quantum computing user program there. And whatever the reason, the collaboration, they allow us to get access to the devices. You can see what I'm talking about. I'm interested in the theory and then the implementation. I want to run calculations. I don't want to talk about what would happen if I could. And I need access. We don't have it. So that's where a lot of the money should be put in the UK. We cannot continue to be dependent on access through other countries. And that's a very important part of it. And it's all the kind of related infrastructures. Don't talk about quantum computing in isolation. From what I said earlier, we need to see it integrated to maximize its benefit, particularly, in the shorter term, because it's so difficult to extract value from it, integrating it with high performance computing and AI type capabilities. So let's not have it just go off on its own direction, but have that integrated into an IT program for advanced research and technology in the UK as a whole.
Brilliant. Well, I've got a follow-on question from Steve Young from Cambridge, who wants to know how many logical qubits will be needed before quantum computers become generally useful, and when might this stage be reached? So, Peter, would you like to pick that up?
Well, I was hinting at that. It does depend a bit on what type of problem you're working at. But this one that's regarded as the killer app, which is to do with quantum chemistry and the solving of the molecular electronic structure problem, which has applications to drug discovery and all the rest of it, we need to be able to do electronic structure calculations in a regime which transcends what is possible today with conventional computers. And I'm saying to you that we need to have of the order of 20 or more of those qubits working together in a positive way that weren't riddled by noise and the other limitations I mentioned. When we are of the order of 20 qubits in that sense, then we would be, as it were, in clear open terrain. We're not there yet, but that's the type of scale we're looking for.
Okay, thank you. And again, one quick follow-on from Paul Shaw, CEO at Loxon Precision. We've talked, Peter, you've talked a lot about the challenges around errors and noise and reliability. And where the question is, what are the key developments that will make the differing types of qubits more robust and noise tolerant?
And that's, again, at the interface between all the theory and the software and the algorithms we do in my team, and then finding the hardware to use. So it's no use just working with IBM and its hardware, as we are lucky enough to. But that's why I'm interested in talking to Oak Ridge, because their program provides access to a lot of other different devices and architectures. So so-called ion trap techniques and a Quantinuum, which is a US company which has a big base now in Cambridge in the UK, has such devices, and their technology is different from the superconducting ones. We have reason to believe that in some respects it'll be easier to do calculations on those. There won't be so much of a noise level, and the error mitigation won't be so severe. We are literally, on the verge of doing that. So you have to be able to look at these technologies and then compare them. And what's better than that is not to just depend on external people, vendors giving you their technology and throwing it at you and using it, but doing co-design, which is identifying manufacturers who want to talk to us about our applications, how they can design the devices so that our applications will run optimally on them. And there are one or two such companies. And I have to say, again, at the moment, for me, they're not in the UK. In this case, I'm thinking of one in Europe. But we work with them and they're the most interesting ones, because they are prepared to design the machines to accommodate our applications. And believe me, at this state of the game, it's really important that that type of work happens.
Brilliant. Thank you, Peter. I think it's a really important point around co-design with manufacturers. I'm going to keep us moving. I want to get through as many of these questions as possible. Melissa, a few sensing ones for you coming in. So from Langyang Liu at Renishaw, we've got how easy to distinguish the disruption from environment other than the actual measurements, and is environmental disruption always a bad thing?
Yeah, fantastic question. Thank you. So I guess the quantum state is a bit selective. It's a bit picky as to what it responds to. So it doesn't respond to every sort of piece of noise. And so, for example, the sensors that working on in my lab responds to magnetic fields, electric fields, like temperature, pressure, and some sort of magnetic type materials. So that's a little bit selective, so we can forget about other things that might interact with it, but we've still got multiple parameters it will respond to. So that's when there's various measurement schemes that we can use to discriminate between if maybe the effect we're looking at is from a magnet or if it was from temperature. So we can fortunately go to the electronic structure of this defect, and we can, for example, control it in a different way, and we can study it over a different set of time points as well. And then we can say, okay, this response, we can exclude other factors, and we could just hone in on the temperature, for example. And the same is true for other quantum sensors as well. They'll have their own sort of sweet spot, if you like, where they respond really well to different environmental conditions. And then there's sort of, in a way, also clever sort of error correction type approaches, as sort of similar that Peter was saying, is using quantum computing, that we can do that can also filter out the noise. So we can do some sort of like quantum lock-in detections, and that sort of lock-in detection system is quite often used in signal processing in many applications. And so we can do sort of like a quantum lock as well to help get the signal we want from the noise.
Brilliant. Thank you, Melissa. You have to give me, I'm talking faster and faster to try and get through more questions. So another sensing question for you: how transferable are current quantum sensing techniques to autonomous vehicle sensing? And that's from Qasim Sadiq, who's an engineer at Warwick Manufacturing Group.
Oh, fantastic. Thank you. Yeah, actually, I think the quantum sensors are quite mature, really, for this sort of area. There's been tremendous strides in developing quantum sensors, which can help with position, navigation, and timing. And so, in fact, people are even looking at, well, actually, groups in the UK, particularly the team in Birmingham, they're looking at some great type of positioning, navigation, and timing sensors. And what they've done is they've done demonstrations in the lab, and now they're making demonstrators. So it's sort of a device. And then I guess the next step, which would be great to bring in people working in manufacturing type of engineering, is now need to make these robustly at scale. So I think we're sort of at the prototype stage and moving towards the sort of reliability testing.
Brilliant. Thank you, Melissa. Now, Melissa, you're also on secondment, aren't you? You're working with government at the moment to try and help them make sure that they have access to a really good understanding of quantum technology and how it relates to government policy. And we've got a policy question here that I'd love to hear your thoughts on, which is from Steve Chapman. Over the next decade, how do you think this will transform the UK job market? Will there be new areas of work and opportunities that we need to be reskilling to take advantage of?
Yeah, thanks a lot, Steve, for the question. Yeah, so I'm fortunate that through the Royal Academy of Engineering, there's a scheme in which I'm placed on a secondment with the Government Office of Science. And it's actually really opened my eyes up to the great work that's done there, and providing independent scientific advice to policymakers. And I think certainly I can speak in terms of what the UK government are prioritising as one of their actions from the quantum technologies strategy is about skills, quantum skills. And so they actually have they're forming a task force at the moment. And I think what's really exciting about that task force is it covers all elements, if you like, of what quantum skills might be. So it's no longer just we're thinking that it's for quantum physicists or theoretical physicists. So this task force is looking to consider apprentices, consider technicians, consider the end users as well. And I don't know if it's included in this activity by the government, but something I'd love to see is involvement of people in the creative industries. So if you think about it, so many people use video gaming, and there's absolutely no reason why you can't have quantum computing based video gaming. The other thing from my point of view with quantum sensing, we sense the world around us, and there's increasing use of immersive technologies in digital art, immersive technologies in reaching out to people, maybe. So I'm thinking about like virtual reality and combating some of the loneliness people have had when they're isolated. And so having quantum sensors feed into technologies like that. So in terms of the workforce, Steve, I think we really need to be thinking about quantum being for everyone, and we need to start making sure we have the voices of the users to inspire our work, because I think that's when the breakthroughs can come, and we can so I've gone off a bit more from not necessarily just the workforce, but I think just saying that this quantum has I think that's where the breakthroughs come, when we collide. You know, in science and engineering, really interesting things happen at interfaces, whether that be a phase change or actual physical interface. And I think in society, it also happens. So if we can bring these communities together, I think that's really exciting.
That's so true, Melissa. Although I have to say, as a mother of a teenager and a preteen, I'm slightly scared about the idea of quantum-powered gaming. Will they ever stop? Right.
That's the question. You must change the coherence. You must hope for short coherence time. One of Peter's computers that is not so coherent.
Well, we'll get back to the audience questions, probably safer. So, Peter, I'd like you to pick up. There are a couple of related questions around the interplay between engineering at large and quantum. So we have a question from Lee Philbin around specific areas of engineering that would be of most benefit from the introduction of quantum technology. And then also a question from Robert Dandridge from NPL around, is it easy enough for engineers to get involved in these exciting developments around quantum?
There are two kinds of questions there. The latter one goes to what skills we require, and as we were saying, the EU has put out some sort of skills set requirements to be involved in quantum technologies, which is a helpful thing we should be posting. I mean, the problem currently is that it is a bit of a closed shop. It's somewhat inward looking. I would say in the UK, it's very dominated by physics and theoretical physicists and stuff, and we see an awful lot of theory stuff being generated. To really make things change, as you can hear from me, we have to get more practical. We have to understand how to deliver these systems in a workable way. Just trivial things like programming, how you handle I/O, input and output onto these devices. This is computing technology in a more general way. I mean, if people were to understand what it takes to make a quantum device produce results, you might be shocked at what's going on. We write circuits. It's a bit like assembly language. It's not a friendly environment at all. We need to be able to design better ways of using the software for these systems. But until we've got big enough devices to do sensible calculations on, we worry more about just making them deliver things in the short term. So, but I'm quite certain, you absolutely need lots of different skills to bring these machines into a practical condition. Then the question of what relevance this has to engineering. Well, in my view, engineering is one of the most dynamic areas we've got going today. It is where all the IT happens, frankly, information technology development. So if you start looking at that, the scope for impact from quantum computing, like AI, is enormous there, and you have to use your imagination to seize the opportunities. It's about trying to get results bigger, better, and faster. It may be to do with the calculations I mentioned for materials and drugs, but it could be the confluence of telecommunications, 6G, and methods that quantum computing can bring to bear to make those technologies work more effectively. So, if you're going to talk like that, you really have to know about the telecommunications aspects of the area you're working in. You cannot do this just as a set of theoretical or even experimental physicists.
Thank you, Peter. And yeah, sorry for smuggling in two not completely identical questions, but you did very well. So one of the topics actually we were discussing before we started the live stream was inclusion in the context of quantum. And as you know, one of the Academy's strategy pillars is inclusive economy. And I was very pleased to see a question from my colleague, Kath, from the Academy, who's asked, how inclusive are quantum technologies? For example, a key barrier to entering this market looks on the outside to be high cost for R&D and startup. Peter, you've made it very clear that only limited people have access to even today's quantum computing capability. And so Kath's asking, are there opportunities for entrepreneurs, SMEs, engineers in the global south, and does the UK have a good regional distribution of quantum technology companies? I guess in the context of sort of levelling up, to use the jargon. So Melissa, I'll start with you on this. I'd love to hear your thoughts.
Yeah, thanks. It's a really important topic, actually, because we don't want to have a situation where we develop bigger gaps between I guess emerging economies and developed economies. So I think important for us as engineers and technology developers that we think about the sort of responsible innovation, and we think about inclusive innovation. So the first thing, because I know there's multiple questions here, so the first thing I'd say is, like, in terms of inclusive innovation, this is where we need to be looking towards where we're manufacturing devices. So I can speak, for example, for quantum sensors, where they can be used by a non-specialist, and you don't need a specialist to fix them when they break. So, I mean, that's one of the big barriers. So say, for example, we've got a device in the lab, and we can sort of fettle it and make it work. And if it goes wrong, we can fix it. So we almost need to have the quantum technologies as like a plug and play. And we also have to have training of of how to fix if things go wrong. We have to have these available in an accessible format. So one of the things I think of, sort of like an analogy of the quantum technology, is, when many years ago when I was younger, and like, I remember as a child sat in front of this computer at school, which was just a marvel. And people, they said they were working in information technology or IT, and this could mean like they were developing machine language, for example. But these days, if someone says they work in IT, they might be the person who's doing it. They might be someone who's at the end of the phone when I've forgot my. So I think to have an inclusiveness of quantum technologies, we have to have an inclusiveness of involvement of stakeholders in that. So I guess that's one of the questions.
Melissa, you're just cutting out very slightly, so I'm going to go to Peter to see if he would like to add anything, and hopefully your sound will come back.
In terms of inclusivity, etc., some of the points we've made already have been raised yet again here, that it is tricky to get access to the capabilities in the UK. If you really want to be touching these machines and delivering stuff, it's not easy. So things have to be done to change that. That 2.6 billion has to address those kind of questions. And the problem for us in many technologies, AI, supercomputing, is the same, is that typically in the UK, we depend on others dishing out what we get and then having to deal with it. And that's not really good enough, because it's just us reacting to external events. If we want to set the agenda, we need to be in possession of more of the technology and try to figure out how best to, as it were, provide the access we require.
Great, thank you, Peter. And Melissa, I think you've got, hopefully you're back and got an additional point to make.
Yeah, thank you. Sorry for that slight dropout. Yeah, so I think another, which speaks to one of the questions that you asked, is I think what's really exciting is the development of 6G, if we think about our telecom systems. So we're now fortunate that many places in the world, and places which sometimes even I would think unexpected, because sometimes I can struggle to get 4G, have amazing coverage of telecoms. And one of the big parts of 6G is envisaged that it will be basically the convergence of technology. So we've got embedded sensors within the telecoms system. So we can think of a time where actually not only in our phone have we got a camera and a light and our calculator that we used to have all these separate devices, but we can now really envisage a future where we could have quantum sensing type devices in these. And what's important about that is then, if we have these in such sort of consumer-based products, then we start to think about how accessible they can be in emerging economies. So I had the fortune to attend the Royal Academy of Engineering event in Ethiopia last year, and I was actually blown away as to how rapidly countries in Africa are taking up digital technologies a lot across finance, across agriculture and health. And I think this could be a real enabler that could see a way where we can, at scale, see a benefit and a sort of, if you like, a global leveling up of access to some of these technologies.
Brilliant. Thank you, Melissa. That's a really positive note to sort of draw the discussion to a close on. I can't believe the time has flown past. I'm going to give you just a moment's heads up that I'm going to ask you each just for a final takeaway, or if there was a point you really would have liked to make but didn't get the chance. You've got 1 minute to do that, so I'll come to you both in a minute. But thank you to everyone who's submitted great questions, and sorry we couldn't get through all of them. So I'll now do the final opportunity for our speakers to land a message with everybody. Peter, would you like to give your final takeaway?
Well, it's really saying the same thing. I don't have anything new to add here. The importance of addressing this as an integrated whole. We need to be able to be masters of the hardware as well as the software, and to then be able to make the innovations that have an impact both in the UK and internationally.
Thank you very much. Nice and succinct, Peter. And Melissa, same from you, please.
Okay. All right. So I think in the UK, we have a national quantum technology strategy that is the envy of many countries. I think, this is a really critical technology, as has been acknowledged. We have a lot of capability, and I think we have to just build the quantum ecosystem so we have it more inclusive. And I think the future is exciting.
Fantastic. Well, I really would like to thank you both for such an interesting and stimulating discussion. We covered so much. You did so well to answer as many questions as you did. And I certainly learned a huge amount, and I hope our audience also feels the same way. It's sort of reassuring that I don't need to understand the details of entanglement and superposition and decoherence to be able to actually connect with what quantum technologies mean for our world. Although I don't know whether to be reassured or slightly worried that even the experts don't necessarily understand everything about quantum. Thank you so much, everyone who's joined us for this session. You gave us some great questions. I always like to make sure our guests work hard, and you certainly did that. And if this conversation has sparked your interest, or if you have further comments about today's event, please do respond to the survey that has been posted in the chat and will be emailed to you following the event as well, because your feedback helps us to shape and improve future events. And as I said at the start, this is the first in a series of critical conversations that's going to look at all of those technologies that were picked out in the UK Science and Technology Framework. We've actually heard, even in today's discussion, some of the interplays, for example, with future telecoms. So do stay tuned. We will have 4 more coming up in the next few months, and the first one will be on semiconductors at 6 p.m. on Tuesday, the 5th of September. We'll post all the information online, but thank you so much again to our brilliant guests and everyone who joined us, and I hope you have a really great afternoon or whatever time of day it is where you are. I hope you have a very good rest of it. Thank you.